Hello everyone. I'm presenting Telekolympographic Swim Gesture Recognition, a natural user interface for aquatic vessel control by Ibrahim Hassan, Rune Sheshdari, Lian Yang, Yuxuan Zhang, and uh, Alexander Vico, myself, under Professor Steve Mann at the University of Toronto. The project asks whether swimming itself can become a control language. Instead of using a joystick or touchscreen, a user performs natural arm motions. A head-mounted camera observes those motions, a vision pipeline converts them into commands, and the same commands control either a virtual boat in Unity or a physical RC boat. Most conventional controllers are designed around terrestrial assumptions, dry hands, a stable posture, and a relatively static environment. Aquatic environments violate these assumptions. The user may be floating, rotating, responding to waves, or continuously changing body orientation. A touchscreen becomes difficult to use, and a handheld controller can interfere with swimming or require the user to stop moving naturally. There is also a cognitive and biomechanical disconnect. The person intends to move through a fluid environment, but that intent must be translated into an abstract button presses or joystick deflections, which are very unintuitive. Water HCI and immersivity motivate interfaces that are native to the environment itself. In this work, we move from a terrestrial paradigm, abstract manipulation imposed on water, to an aquatic paradigm based on embodied interaction. The design question is therefore not simply how to waterproof an ordinary controller, it is how to use the movements that are already make sense in water as the control vocabulary. The proposed interface begins with egocentric capture. A camera mounted on the user's head records the upper body and arm motion from the swimmer's own viewpoint. The vision pipeline segments the arms, extracts geometric contours, tracks their motion, and converts that motion into actionable commands. The mapping is designed to be intuitive. Asymmetric arm strokes determine steering direction, and if the right side motion dominates, the system commands one steering direction. If the left side motion dominates, it commands the other. More symmetric forward stroking generates propulsion. The same gesture to command mapping is used in two domains, a Unity simulation and a physical RC boat. This is important because the interface logic is not tied to one particular vehicle model. The image on the side shows the original egocentric frame and resulting arm mask. The goal is to preserve the natural meaning of the movement while converting it into a compact machine-readable control signal. Each input frame begins in BGR color space and is converted to HSV. HSV separates hue and saturation from brightness, which makes color thresholding more manageable under varying illumination. Before thresholding, a 5x5 Gaussian filter with sigma equal to 1.1 reduces high-frequency image noise. A skin tone mask is then formed using a fixed HSV bounds. The lower bound is 0, 80, 80, and the upper bound is 20, 150, 255. Because the surrounding scene may contain colors that overlap with the skin mask, the pipeline also creates green and gray exclusion masks. These are combined and subtracted from the candidate skin region to reduce background interference. Finally, morphological filtering cleans the binary image. One erosion pass removes small noise regions, and 3 dilation passes restore continuity in the arm shapes. The diagram on the right summarizes the sequence from input frame to smoothing, color conversion, masking, exclusion, erosion, and dilation. After preprocessing, contour analysis converts the binary arm regions into steering and thrust commands. The Suzuki-Abe border following algorithm extracts contours from the cleaned mask. Douglas-Purger polygon simplification then reduces contour complexity while retaining the main shape. The two largest contours are selected as the left and right arm candidates. Because frame-by-frame centroid measurements can fluctuate, exponential smoothing with a beta parameter stabilizes the motion estimates. Steering is based on a normalized stroke asymmetry index. Conceptually, the system compares right arm motion with left arm motion and divides their difference by their combined magnitude plus a small epsilon, so that we don't divide by 0. Positive and negative values indicate opposite steering directions, while values near zero indicate more symmetric motion. Forward thrust is driven by the average propulsion score across the two arms. This is deliberately lightweight geometric method rather than a large learned gesture model. The advantage is that the mapping remains interpretable, arm symmetry controls steering, and shared forward motion controls propulsion. The hardware is designed for hands-free and mobile operation. A head-mounted HD webcam is attached using an adjustable elastic strap, providing the egocentric view without occupying the user's hands. A Raspberry Pi 4 Model B with 8 gigabytes of memory runs the vision pipeline and acts as the compact processing hub. The physical RC racing boat contains an ESP8266 based Wi-Fi communication layer, motor drivers, and LiPo battery, lithium polonium battery. Commands are transmitted through a local UDP connection to minimize control delay. In parallel, Unity model of Peter Street Basin provides a virtual test environment. It was built from three-dimensional scans and photogrammetry and includes custom buoyancy and drag behavior. The result is a single sensing and processing setup that can drive either a simulated vessel or a real boat. This slide emphasizes portability across domains. On the left is the Unity simulation of Peter Street Basin. The virtual environment supports repeatable testing and allows the gesture interface to be evaluated without immediately depending on weather, water conditions, or physical boat availability. On the right is the physical RC boat, which is a racing boat with its Wi-Fi communication layer, battery, and motor control hardware. The same gesture to command mapping controls both. No retraining or reconfiguration is required when switching between the virtual and physical domains. This separation is useful for development. Changes to the vision pipeline can first be tested in the simulation, and the same command logic can then be applied to the real platform. More broadly, the result supports the natural user interface concept. The interface is defined by the user's embodied motion, not by the details of a single simulated or physical vessel. We evaluate two main properties, command accuracy and end-to-end latency. For accuracy, the primary criterion is whether the system outputs the correct control state, left, right, or straight, at the maximum stroke speed represented in this test sequence. The evaluation uses the controlled videos labeled V1 through V4, together with the real-world freestyle video labeled V5. This allows comparison between cleaner laboratory conditions and more natural swimming motion. For latency, the Raspberry Pi 4 serves the processing hub and local wireless access point. Vision processing time is measured using Python timers, and network delay is measured using T-Shark. The total delay is defined as the sum of vision time and network time. This division matters because it tells us whether responsiveness is limited primarily by image processing or by communication. That distinction directly informs future optimization. In the controlled videos, command accuracy ranges from 75% to 94.7%. The individual results shown are approximately 88.8% for V1, 75% for V2, 94.7% for V3, which is pretty high, and 82.6% for V4. On the natural freestyle video V5, the system reaches around 81.6% accuracy. This indicates that the simple contour-based pipeline retains useful performance outside the most controlled conditions. Mean total latency is 175.37 milliseconds. Of that, vision processing accounts for 66.97 milliseconds, while the network contributes approximately 108 milliseconds. The latency plot shows that the largest variation comes from network spikes rather than from the core vision computation. And despite those spikes, the system remained responsive enough for proof of concept interaction control. The results therefore establish feasibility, but they also identified the dominant engineering weakness, which is where we need to improve. Improving communication consistency may provide a larger responsiveness gain rather than making small reductions to the vision processing time. So again, these are very large computer vision realizations that we're making. To conclude, this project demonstrates real-time swim gesture recognition for both virtual and physical boat control. The main contribution is an aquatic natural user interface that uses motion already native to swimming. A head-mounted camera observes the arms, geometric image processing extracts the movement, and a transparent mapping converts asymmetry into steering and shared motion into propulsion. The same interface operates in Unity and on a RC boat, demonstrating portability across virtual and physical environments. The main current limitation is network reliability under variable wireless conditions, which is to be expected, and the average latency is acceptable for a proof of concept, but network variation creates spikes that reduce consistency. Future work would therefore include more deterministic communication and timing control. The vision method can also be strengthened with contour eccentricity and convexity features to improve arm identification when masks are fragmented or distorted. Finally, the system requires a larger pool-based evaluation with users operating under true water immersion conditions. The broader message, sorry, is that aquatic interaction should not only comply and copy interfaces designed for dry land. By treating swimming as a control language, we can build vessel interfaces that are more embodied, intuitive, and native to the environment. Thank you very much for listening.